Hello and welcome back to Introduction to Number Theory. I'll remind you that we are studying quadratic irrationalities and Bell's equations. And in this video, which is called The Meaning of Signs, you must be asking yourselves, what signs? Why do we need to know the meaning of these signs? Well, let's consider quadratic irrationality with norm equal to 1. This means that z is equal to x plus y square root of a, and at the same time x squared minus a y squared is equal to 1. This is the famous Bell's equation, where a is a given number, integer that is not perfect square, and x and y are unknowns in this equation. Of course, the norm of z and this expression x squared minus a y squared, they're the same. So x and y, both of them can be positive, can be negative. Some of them may be equal to 0. Well, of course, if y is equal to 0, then x is equal to plus or minus 1, and this is a trivial solution to the Bell's equation, and it's not interesting. And if y is not equal to 0, then certainly x is also not equal to 0, and each of them is either positive or negative. So now I would like to discuss what these signs of x and y impact. It turns out that we can use the signs to determine the set to which z belongs. The answer to our question, what do these signs impact, is given in the following table. Let's focus our attention on this table. Well, we see that if x and y are both positive, which is denoted by plus plus, well, we understand that then z is greater than 1, and it's obvious. But in the same table, we see that if x is positive and y is negative, then z is for some reason positive but less than 1. Well, this is not so obvious. Why, if x is positive and we subtract from x y multiplied by square root of a, why is the result positive? And why is it less than 1? Also, if x is negative and y is positive, the third row in our table, then z is between minus 1 and 0. Also not obvious. Well, of course, if x and y are both negative, then it is obvious that z is less than minus 1. So let's prove these non-obvious rows of our table. First, transform the Bell's equation into a product of two parentheses, x minus y square root of a and x plus y square root of a. And now notice that first, both factors should be of the same sign, since their product is positive. So either both factors, both parentheses, are positive, or they are both negative. Well, at least this explains why, if x is positive and y is negative, then z must be positive, because with the positive y, z is greater than 1. It's the first row of our table. So if y is negative, then z must at least be positive. The same with the negative case. Second observation is that if one of these factors, if its absolute value is less than 1, then the absolute value of the other factor is greater than 1? Well, since their product must be equal to 1. And this explains why if x and y, both positive, give us z greater than 1, then x positive and y negative give us z less than 1. Because their product, the product of expressions x minus y squared of a and x plus y squared of a must be equal to 1. So one of them is greater than 1 and the other one is less than 1. And the same in the case where x minus y squared of a is greater than 1 and x plus y squared of a is less than 1. So one of the parentheses is greater, the other one is less.